Good evening, class. I am Mohit, and this is the TA class for assignment number 8. And there will be 10 questions which belongs to Electronic Theory of Solids course. These assignments are from 2024 course and are set to be solved for 2025 demonstration. So there will be 10 questions, and I'll be solving the 10 questions so that one can get the idea of how to approach these kinds of the problem, which will eventually help in the examination and also in understanding the concepts better. So starting from the first question, which says that the saturation magnetization Ms is the maximum magnetization obtained when all the magnetic moments are aligned, so that Ms is equals to n mu, where n is the number of moments per unit volume. However, at any finite temperature, the actual magnetization of the system is given by m is equals to n average of mu z, but the correct expression for the susceptibility according to semi-classical paramagnetism. So let's start and solve this question. So according to question, let's consider a system of n magnetic dipoles per unit volume, and each has a magnetization mu. Now magnetic field H will align the magnetic moments leading to magnetization M. At finite temperature, the alignment is not completely because of the magnetic field, but also gets disturbed by the thermal fluctuations. So now let's say that, so this is the step 1, these are the assumptions. At finite T, the alignment is not complete due to the thermal fluctuation. So these are the problems these are the system which we have. Now in step 2, let's write the energy in terms of the magnetic field. So potential energy in terms of magnetic field, in terms of H. So potential energy in terms of magnetic field is mu H minus mu H cos theta, where theta is angle between magnetic moment mu and H. H is the field, magnetic field. Now we'll have to look at the Boltzmann distribution, how the probability of finding a magnetic moment at an angle theta is. So what is the probability of finding a moment at angle theta? So that will be step 3, Boltzmann distribution. The probability of finding a particle at any theta is e to the power mu h cos theta by kbt times cos theta by z. Z is the partition function. T is temperature, Kb is Boltzmann constant, and Z is the partition function for normalization. And Z is given by 0 to pi e to the power mu h cos theta by kbt times sin theta d theta. And if you solve it, substituting x cos theta equals to x, this implies minus sin theta d theta equals to dx. And thus gives this equals to 1 minus 1 to 1 e to the power mu h x by kbt times dx. And if you solve it, it will give you kbt by mu h e to the power mu h upon kbt minus e to the power minus mu h upon kbt. So, and you can write this as sine hyperbolic. So it will turn out to be 2 kbt by mu h times sine hyperbolic mu h by kbt. Now this is the partition function. Now we have the partition functions. We can substitute in this p theta. So let's now look at the average magnetic moment. Average magnetic moment. So this will be step 4. Step 4. Average magnetic moment will be mu times cos theta. Mu, that is the magnetic moment speed by cos theta. So you do it. How you do it? You integrate it from 0 to pi cos theta e to the power mu h upon kbt sin theta d theta by, so this is integration, and then z. So you solve it by substituting x is equals to cos theta. This will turn out to be mu times minus 1 to 1 x e to the power mu h x by kbt dx by z. And if you solve this one, this solve it. To solve this integral, it will turn out to be mu times Langevin function. So Langevin function mu h upon kbt, where Lx is Langevin function and so Lx is equals to cot hyperbolic x minus 1 by x. That's what this means. Now we have got this P. So now for the low field approximation, where temperature is very high and the field is less. So step 5, low field approximation. What will happen? You can write Lx as low field approximation means mu h by kbt is less than 1. So this will be the P. If I write mu h by kbt, and if I write it, will be equals to mu times cot hyperbolic mu h by kbt minus kbt by mu h. For this approximation, this P will be approximately mu times cot hyperbolic x is kbt by mu h plus mu h by kbt 3 minus rest higher order terms. There are higher order terms order of by mu higher. These you neglect, minus kbt by mu h. So P is mu square h by 3 kbt. Now we know the relation between magnetization and susceptibility. The total magnetization M will be there, since there are n number of such n number of particles per unit volume. So n times is P. Step 6, magnetization. M will be equals to n times this, which will give you n mu square h by 3 kbt. And we know the magnetic susceptibility. Susceptibility is nothing but m over h. That will be n mu square by 3 kbt. Let's see if there is an option like this, n mu square by 3 kbt. So the option number 2 is the correct answer. So in this question, what we did, initially we looked at what the problem says, that there is n magnetic dipoles per unit volume. External magnetic field applied is H, and T is the final temperature. Since the dipoles will not be perfectly aligned, they will be having thermal fluctuations, so they will be at some angle theta with respect to the magnetic field. In that case, your energy will be given by minus mu h cos theta, and then the probability of finding the particle at theta will be e to the power mu h cos theta by kbt times cos theta by z, where z is the partition function. We calculate the partition function, and that turns out to be this 2 kbt mu h sine hyperbolic. Now we look on the average magnetic moment semi-classically. That's what the question asks. So mu average over cos theta. So we calculate that value, and that turns out to be mu times Lagrange function of mu h by kpt. For small h and large t limit, we expand it, and what we get is the average magnetization is mu square h by 3 kbt, n times mu square h by 3 kbt, and chi is magnetization by applied magnetic field, and we get the value of chi to be n mu square by 3 kbt. Now moving on to the next problem, which is consider the vapor to be an ideal gas. Find the paramagnetic contribution to the Curie susceptibility of cobalt, which forms an atomic vapor at 1768 Kelvin in units of centimeter cube per mole. Bohr magneton is given, Boltzmann constant value is given, Avogadro number is given. Hint, you can calculate the Landesi factor for cobalt atom, and the formula for the Landesi factor is also given. So it's an easy problem to deal with. We know that Curie susceptibility is given by chi molar equals to Na is Avogadro number, G mu B square by 3 J plus 1 by KBT. Okay, and G is also given. G is S plus 1 minus L plus 1 by 2 J plus 1. Okay. Now cobalt is given. So material is cobalt. With CO, Z equals to 27 and 3D7. For S, L is equals to 0, P, L is equals to 1, and for D, L is equals to, okay, here if you see, this is L, So here in the D cell, one can fill up to 5 unpaired electrons. So D is like this, right? 1, 2, 3, 4, 5, 6, 7. So spin is what? S is 3 by 2. L is 3. That gives you J is equals to L plus S. That will be 3 plus 3 by 2. That will be 9 by 2. 4.5. Now let's just substitute these values in equation 1. This is equation 1, this is 2, this is 3. Substitute in 2. G is equals to 3 by 2 plus S is 3 by 2, 5 by 2 minus 12 by 2 into 9 by 2, 11 by 2. G is 3 by 2 plus 15 by 4, 48 by 18 into 11 by 4, 4 goes. G is 3 by 2 plus 48, 15 minus 48, 15 minus 48 is 33, 18 times 11, 3, 1 by 6, 0.16, this will be minus, so 1.5 minus 0.166, 1.5 minus 0.166 will be nothing but 1.334. So that is the value of the G. G is 1.334. Now this is equation 4. Substitute equation 4 into 1. Substitute equation 4 in the silver Remember, J is 4.5. Avogadro number is 6.022 into 10 power 23. G is 1.334 into mu B is Bohr magneton is 9.27 10 power minus 21 square by 3 times J is nothing but 9 by 2 is 4.5. 9 by 2 times 11 by 2 by kBT is kB is Boltzmann constant whose value is 1.38 into 10 power minus 16 arc per Kelvin, and temperature T is, in the question it is given to be 1768. If one solves it, one will get the answer to be 3.11 into 10 power minus 3 centimeter cube per mole. The answer. It matches very well with option number 4. Three point 11 into 10 power minus 3 centimeter cube per mole. Now moving on to the next question, which is if there are n moments in the system non-interacting with each other, then what is the expression for the free energy F and the mean energy of the system? So for this one we'll have to first write the partition function for the system, and then from the partition function we'll know that how to write the free energy and the mean energy. So let's write the system and partition function. System and partition function. We have n non-interacting moments, right? And each has magnetic moment mu, with each having magnetic moment mu. So possible energy states is like either it's plus mu b or minus mu b. So these are the two possible ones. Right? So the partition function z is equals to e to the power beta mu b plus e to the power minus beta mu b, and this will turn out to be 2 cos hyperbolic mu b beta mu b. Here beta is, we know that 1 by kBt. For n independent moment, the partition function will be zi to the power n, z1 to the power n. So this is for the one. For if there are for n independent moments, the total partition function z will be z1 to the power n, and that will be 2 cos hyperbolic beta mu b to the power n. Now let's look at the and now we have the partition function, so we can easily calculate the free energy and the mean energy. So free energy, also known as the Helmholtz energy. So step 2 for our case will be free energy calculation. by F. So the Helmholtz free energy F F is equals to, the formula goes like minus kBT ln Z, which is the partition function. So if you put it like this, so it will be minus n kBT ln 2 cos hyperbolic beta mu b. So this is the free energy for the system. Now the problem asks, what is the mean energy? Mean energy is nothing but minus del ln z by del beta. Mean energy E is nothing, E tilde, mean energy E tilde is equals to minus del ln z by del beta. So if you do it, minus del by del beta of minus n k bt ln 2 cos hyperbolic beta mu b. So E will turn out to be minus n times 1 by 2 cos hyperbolic beta mu b, and the derivative of the cos hyperbolic beta mu b, that will turn out to be 2 mu b sin hyperbolic beta mu b, and this will give like mean energy to be minus n mu b tan hyperbolic beta mu b. Let's see if there is any option. E is minus n mu b. Here instead of b you can write h also, because h and b both are same magnetizing. So E is minus n mu b tan hyperbolic. So tan hyperbolic is either 3 or 4. Now let's look at the option of the F. F is cosine. So the correct answer is 4. The correct answer is 4, that minus n kBT ln 2 cos hyperbolic beta mu h, and the free energy is to be minus n mu b tan hyperbolic beta mu. These are the correct options for it. Yeah. Now moving on to the next problem, which is problem number 4. The question says that if M is the magnetization of an Ising ferromagnet, where Hamiltonian is H is equals to minus J summation over Ij, Sij, and J, Sjj, I and J are the nearest neighbors, then which of the following can be the free energy of the system? So now let's first look at the Hamiltonian. H is nothing but minus J summation over Ij, Sij, I and J are the nearest neighbors. So if I apply a magnetic field in this direction, that all my spins are up, in that case my Hamiltonian for all up spins, let's say Sij and Sjz both are in the up direction, plus half and plus half, let's say. So that in that case, this is an example, plus half and plus half, so it will be minus J by 4, right? And H Hamiltonian for all spins down, also it will be minus J minus half into minus half, so minus J by 4. This means Hamiltonian is invariant change in spin. Change in spin. What does it mean? I mean h of s is equal to h of minus s. This implies m, which is given the system, m of s is equal to m of minus s. And if this is the case, if your Hamiltonian is not changing, energy will not also change. So if you change the m, then your f should also not change. If you replace m by minus m, then then for your system also your f should not change. F basically your so what does it mean? It means that m is equals to 1 by n I s I z, right? For change in spin, your m will be minus 1 over n, right? If you just multiply both sides by negative sign. So this is like change in spin. And both m and minus m should give you the same f. This implies f has to be even function of m, and if you look at the even functions, only option A satisfies the condition because here the power is 3, here the power is 3, here the power is 3. They are all even powers. So option A satisfies the condition that your f equals to f0 plus am square plus bm to the power 4. The energy should not change if you change the spin. Basically, that's what it means. So answer number 4 is also, question number 4 is also addressed. Now moving on to the next question, which is which of the following has or have s is equals to j. Okay, we know that j is equals to, we know j is equals to L plus s. J is where j is total angular momentum. This is orbital angular momentum. And this is spin angular momentum. Now, for j is equals to s, this implies L has to be 0. So for whatever material they have given, ions of material, if L is equals to 0, that means in the system j is equals to s. So okay, let's analyze them one by one. Let's take the first case. Here m is given with z is equals to 25. Right? So if for this one, the electronic configuration we can write. We can write to the argon, and after argon there are 3d5 and 4s2. That's how it is filled. In the ground state, so if I just go like this, 3d5 and 4s2. This is the configuration. So in the ground state, 3d5, the 5 electrons are half filled. Configuration. What does this mean? That in the ground state, the 5 electrons are in the half field configuration. So a spin quantum number S is equals to 5 by 2. Since each electron contribute half and there are 5 unpaired electrons, so it will be 5 by 2. And your orbital angular momentum L will be 0 because for the half filled subcells L is equal to 0. L is equals to 0 from Hund rules. For half filled. Since L is equals to 0, this implies J is equals to S. So this is true for Mn. Now let's look at the second material, which is iron Fe3 plus, which has Z is equals to 26. Electronic configuration you can write configuration will be argon, and on top of that there will be 3d5, 3d6, 4s2, 4 iron, for Fe, for Fe3 plus. This will be argon, 3d5. That's it. Because it will lose the first 2 electrons from the 4s2 and 1 electron from the D cell. Right? So the configuration will be, then it's similar to Mn. Right? So it is like argon is there, and in the D cell you have 5 unpaired electrons. You have 5 unpaired electrons. 1, 2, 3, 4, 5. So your spin number will be 5 by 2. Your L will be 0. This simple. Your J is equals to S. Now the option number 3, which is given. Let's analyze that one also. So option number 3, which is given in the problem, is cobalt, Z equal to 27. For Z equals to 27, the electronic configuration is nothing but argon, and then 3d7, 4s2. So here, if I draw its electronic configuration, so it will be argon, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. This is 3d7, and then this is 4s2. So here, if you see, there are 3 unpaired electrons. So S is equals to 3 by 2. Your L will be, in this case, L is not equal to 0 because it's non-zero for partially filled d orbital. L is not equals to 0. This implies J won't be equals to S. So the correct options here will be the first and the second, Mn and Fe3 plus. Because once the L is not equal to 0, then J will be given as from L minus S modulus to L plus S modulus, all the values. And in that case, J won't be equal to S. And therefore, for cobalt, J is not equal to S. For others, for Mn and Fe3 plus, it is equals to J is equals to S. Now moving on to the problem number 6, which is nickel forms a atomic vapor at 2000 Kelvin. You can consider this vapor to be an ideal gas. What is the paramagnetic contribution to the Curie molar susceptibility of this gas at 1000 Kelvin in SI unit? We have solved the similar problem, but I will solve this one also. So We have solved a similar problem, but let's solve this one. Nickel. So the Landage factor, first we have to look at the Landage factor, which is given as 3 by 2 plus S plus 1 minus J minus L plus 1 by 2J plus 1. L plus 1 by 2J plus 1. Right? For nickel, Z equals to 28. So let's write its electronic configuration. So for cobalt we have already written, right? So for cobalt we have written it to be this one. So it will be 3D8. And this is nickel, Z equals to, so this is argon, 3D8, 4S2, right? So your spin S will be, your S spin will be half plus half, that will be 1, because of these two, they are unpaired, and L will be 4 plus 2 minus 1 minus 2, that is 3. So J is equals to L plus S in this case for more than half filled. So the J is equals to 4. And if you substitute these values in equation 1, S is 1, 1 plus 1 is 2, minus L is 3, 3 plus 1 is 4, divided by 2, 4, 4 plus 1, 3 by 2 plus 2 minus 12 by 8 into 5, 3 by 2 minus 1 by 4 is nothing but 12, 12. So this will be nothing but minus 4, minus 8. This will be G is equal to 5 by 4. Yeah. Now Curie susceptibility. Let's write the Curie susceptibility. Chi molar is equals to Na times G mu B square L J plus 1 by 3 kBt. That's the formula. Now let's substitute the values. Chi molar equals to Na is 6.022 into 10 power 23 mole inverse. G is 5 by 4. Mu B is Bohr magneton, whose value is 9.27 into 10 power minus 24 square. J is 4. 4 into 5 by 3 kBt3 into kb is Boltzmann constant, 1.38 into 10 power minus 23, and temperature is 1000 Kelvin. If you solve it, the chi molar, it will turn out to be 3.906 into 10 power minus 2 in SI units. Meter cube per mole. So that will be the answer to this problem. Yeah. This is the correct option, 3.906 into 10 power minus 2. Now moving on to the problem number 7, where the question says that magnetic susceptibility of a diamagnetic material can be. We know for diamagnetic material, magnetization is equals to chi of H for diamagnetic material, chi equals to negative. This implies option number 2, which is negative. For others are positive, they can be true for the paramagnetic and the ferromagnetic material. But for diamagnetic material, chi has to be negative. That's what the definition of the chi is. Now moving on to the next problem, which says the diamagnetic susceptibility of an atomic xenon, assuming that R square is approximately A naught square. A naught is the Bohr radius, 0.529 into 10 power minus 8 centimeter, or 0.529 angstrom. And they are asking the value of diamagnetic susceptibility in terms of CGS unit. So let's just calculate. So we know chi molar is nothing but minus Z. Z is the atomic number. E square by 6 mc square. Na is Avogadro number, averaged over R square. Where for xenon, Z is equals to 54. E is electronic charge, 1.6 into 10 power minus 19. M is nothing but 9.1 into 10 power minus 20 minus 31 kg. This is Coulomb. Then speed of light, C is 3 into 10 power 8 meter per second. N is Avogadro number, which is 6.02 into 10 power 23 mole inverse. And R is nothing but is equals to A naught, that's given in the question, 0.529 into 10 power minus 10 meter. If you substitute all these information here in this problem, you will get chi molar, and whose value will be minus 42.66 into 10 power minus 6 centimeter cube per mole. That is the answer, minus 42.66 into 10 power minus 6. So this will be the correct option, option number 3. That is the correct option. Now moving on to the next problem. A system of n non-interacting spins with spin value s has total entropy equal to. So first we have to write the partition function, and then we know that kbtl and z is that you will have to write the total number of states. When you know the total number of states, entropy is given as kbt, Boltzmann constant, log of the total number of states. So total number of states omega is equals to 2s plus 1 to the power n, because there are n non-interacting particles, and spin value has s, so the corresponding values will be 2s plus 1. So the total number of states will be 2s plus 1 to the power n. And entropy S is equals to nothing but Kb ln omega. That will be Kb and ln 2s plus 1 and Kb ln 2s plus 1. That will be this. Now moving on to the last problem, which is the problem number 10, which says an organic molecule has its triplet S equals to 1 excited state at energy delta above the singlet state S equal to 0 ground state. Which of the following statement is true for T when KBT is larger than this delta, where delta is the excited state energy above the singlet. So first we'll have to write the partition function and then we will see it how the things goes. So for S is equals to 0, Sz will also be 0 because it can take value 2s plus 1. Since S is 0, so it can take one value, that will be Sz equals to 0. And for S is equals to 1, Sz can take three values, minus 1, 0 and 1. Partition function for this system, will be Z is equals to summation over all states e to the power ei by kbt. That's what it is, right? Eis, all Eis. Here Ei will be nothing but it will be like minus, it will be nothing but mu b, right? Here Ei, so E is given as 0, where the ground state energy will be mu times h, right? Basically mu times p, you can say. If your, so if your mu is 0, so E0 will be 0, 4, and E1, E minus 1 will be nothing but delta minus mu b. E0 will be nothing but delta. This is the ground state, first excited, delta plus mu b. In that case, you write the partition function to be e to the power 0 plus e to the power minus delta minus mu b by kbt plus e to the power minus delta by kbt plus e to the power minus delta plus mu b by kbt. So z will be nothing but here mu is 4 magneton, kb is Boltzmann's constant, and T is the temperature. Okay, so your Z will be 1 plus e to the power. Now some assumptions are also given. Let's take them. KBT is very large than delta. So for that case, KBT is very large than delta. In that case, Z will be 1 plus e to the power minus it's mu b by KBT plus this will also KBT is very larger than delta for KBT very larger than delta. This will also turn out to be 1 plus e to the power minus mu b by kBt. And if I take applied magnetic field is also less kBt, then z will be 1 plus 1 plus 1 plus 1, that will be 4, the partition function. And magnetization is given by Es is equals to minus mu Sz B. Magnetization M is equals to mu 1 over Z summation over all Sz e to the power minus E Sz by kBt. That will be nothing but mu 1 e to the power mu b by kBt plus minus 1 e to the power minus mu b by kBt, because for energy equals to 0, Sz is equals to 0, that is for this state and this state. Anyway, this term is there, so it will cancel out the things. Only the plus 1 and minus 1 state will survive. And by Z, so magnetization will be nothing but mu 1 plus mu b by kBt minus 1 plus mu b by kBt by 4. Z is 4, we have already solved it, so it will be mu square b by 2 kBt. That will be the magnetization. And since m is equals to chi times h, chi times b, this implies chi is equals to mu b by 2 kb, mu square by 2 kBt. Let's see if there is an option like this. Okay, now it's asking how the chi depends on the T. So chi goes inversely with temperature. That's what it means. Now let's just revise the problem which we have solved in this class. Starting from the first problem, the saturation magnetization field Ms was given. So they say that Ms is the saturation magnetization field when all the dipoles are aligned in one direction. But at finite temperatures, this won't be the case. At finite T, there will be some will be here, some will be like they will be doing random motion. And if this the applied magnetic field, theta is the angle between them, then in that case energy will be given by mu h cos theta. Now the probability of finding a dipole at angle theta is given by this relation, e to the power mu h cos theta by kBt cos theta by z, where z is the partition function. So first we calculate the partition function. Partition function is e to the power minus energy by kBt, energy we write minus mu h cos theta, then integral over all space, the full space, basically this space from 0 angle to pi angle, full angle 0 to pi. We substitute cos theta equal to x, that gives the minus sin theta d theta equal to dx. We solve this integral, and this gives the partition functions to be 2 kBt by mu h sin hyperbolic mu h by kBt. So that's the partition function. Now average magnetic moment we have to calculate. So averaging magnetic moment is magnetic moment, the cos component of the magnetic moment basically. So mu cos theta, and then the probability of finding that particle point to the power mu h kBt sin theta d theta by z. We do this integral. This is given as mu times the Langevin function of mu h by kBt. Langevin function is cot hyperbolic x minus 1 by x. We expand the code hyperbolic x for this limit, for the given limit mu x by kbt is less than 1, and what we get is p to be mu square h by 3 kbt. Since the total magnetization will be density of such carriers, so density of such magnetic moment n times this probability of finding these particles at point, so n mu square h by 3 kbt, and your chi will be given as n mu square by 3 kbt. So that's the correct answer for this problem number 1. Now for problem number 2, consider the vapor of an ideal gas. Find the paramagnetic contribution to the molar Curie susceptibility of cobalt, which forms an atomic vapor. Temperature is also given. Bohr magneton value is given. Boltzmann constant is given. Avogadro number is given, and how the Landage factor will change depending on S and J is also given as J and L. So first we calculate the Landage factor for cobalt. For cobalt, 3 unpaired electrons are there. So S is equals to 3 half and L is equals to 3, which gives J is equals to 9 by 2. We substitute all three value in this equation number 2, and what we get, G is equals to 1.334. We substitute this value 1.334 and the mu b, kbt, J values, Avogadro number in equation number 1, which gives the Curie susceptibility for the paramagnetic material, and we get the correct answer to be 3.11 into 10 power minus 3 centimeter cube per mole. Now moving on to the next problem, which says that if there are n moments not interacting with each other, then what is the expression for the free energy F and the mean energy E? Okay, so first we write the partition functions for non-interacting particles. So if they have they can have the possible energy states to be mu b or minus mu b, depending on the direction of the magnetic field also. So the partition function is beta mu b plus e to the power minus beta mu b, which gives the 2 cos hyperbolic beta mu b, where beta is 1 by kbt. Now for n independent moments, it will be z1 to the power n. And so this is z. Free energy, we know that its free energy is given by minus kbt ln z. Partition function we know, we take the logarithmic of this, and that gives the free energy to be minus n kbt log of 2 cos hyperbolic beta mu b. Similarly, we can also calculate the mean free energy, E tilde, that is given as minus del by del beta of ln z, and if we calculate it, the correct answer turns out to be n mu b 10 hyperbolic beta mu b. So that's the answer for the mean energy, and that matches very well with the option number 4. Yeah. Now moving on to the problem number 4, which says that if M is the magnetization of an Ising ferromagnet, when Hamiltonian is given by this relation, I and J are the nearest neighbors, then which of the following can be free energy for this system? So if we flip the spin sign, all the spins are up aligned or down aligned, then Hamiltonian is invariant. In that case, if I change spin here, n goes to minus n, but my energy is not changing. That means my f should also not change. Means f has to be an even function of n, and option 1 only satisfies the criteria, so that only option 1 can be the correct answer. Now the problem number 5 is like, which of the following has S is equals to J, Mn, Fe3 plus and cobalt. We know for having S is equals to J, L has to be 0 because J is equals to L plus S. We'll look for the electronic configuration of Mn, Fe3 plus, and what we find is that here this has the 3 unpaired electron, which is half, and the D cell is half filled, so that the L will be 0 in this case. Similarly, here also the L will be 0, and if the L is equals to 0, that means the J is equals to S for that case. And for the last cobalt one, L is not equals to 0, L can take value. L can take a finite non-zero values, and J will be L minus S to L plus S in that case. Now, moving on to the problem number 6, nickel is given, which forms an atomic vapor at 2000 Kelvin. You can consider this vapor to be an ideal gas. What is the paramagnetic contribution to the Curie susceptibility for this gas at 1000 Kelvin? Okay, so in the problem, we know that we have to calculate the G Landage factor. Similarly, what we have done above also, same formula goes. We calculate the spin is 2 into half that is 1, and L is 4 plus 2 minus 1 minus 2, that will be 3 in that case, and J is 4, that gives Lagrange factor to be 5 by 4, and Curie susceptibility is given by this relation. We substitute all the values there, and what you find is chi molar to be 3.906 in 10 power minus 2 metric cube per mole. Moving on to the next problem, which says that the magnetic susceptibility of a diamagnetic material can be. We know that for the diamagnetic material, chi is negative. So the option 2 is the correct answer for this. To the problem number 8, the diamagnetic susceptibility of atomic xenon, assuming R square approximately equal to A square. We know that chi molar for diamagnetic susceptibility is given by this relation, minus Z E square by 6 mc square Avogadro number times average of R square. For xenon, Z is equals to 54, E is electronic charge 1.6 10 power minus 19, M is the mass of electron, C is speed of light, N is Avogadro number, and R is the Bohr radius. We substitute all these values, and what we get, the answer to be minus 0.42, 42.6 into 10 power minus 6 centimeter cube per mole. Now moving on to the problem number 9, a system of n non-interacting spin with spin value s. If some system has spin value s, total number of states will be 2s plus 1, and if there are n non-interacting electrons, then it will be 2s plus 1 to the power n. You take log of it and total number of states, and that will give you the entropy of the system minus that kbl log of the total number of states, and the total number. This gives the kbn ln 2s plus 1. This is the correct answer, A. Now, moving on to the next problem, an organic molecule has its triplet S equals to 1 excited state at energy delta above the singlet S equals to 0 ground state. Which of the following statement is true for temp T when kBT is greater than this energy splitting? So for S is equals to 0, Sz will be 0 because it can take 2s plus 1. S is 0, so that will be Sz equal to 0. Circular shape basically. And for S is equals to 1, Sz can take value minus 1, 0 or 1 depending. Now we write the partition function. Partition function is like this only. So Z is equals to, Z is, if you put the approximation, Z will be equals to 4, 1 plus 1 plus 1 plus 1, that will be 4. And if mu B is less than kBT, and Z is equals to 4, magnetization is given by minus mu SZP, then you estimate this value for SZ equals to 0, that is for the ground state, and the one state of the excited state also, this term is 0, so only the plus mu B and minus mu B term survives, and in that case what we get is M is mu B square by 2 kBT. Since magnetization is directly proportional to the B with a proportionality constant of susceptibility, so susceptibility in this case will be given by mu square by 2 kBT. So the correct answer here is that chi goes as inverse of T and not T plus delta of T minus delta. That's the correct answer here. Yeah. So with this is in this class. In the next class will also be on the susceptibility, the magnetic properties of the system, paramagnetic material and all those things, which will be on Monday 6 p.m. That is today's Friday, so next Friday 21st. So it will be on Monday 6 p.m. So let's meet on that class. If you have any question or doubt, you can ask me in the comment section. I'll be happy to address your concerns. there are no more questions, then I will conclude the class. Thank you for attending it.